Some of you guys are early. Good job. All right, well, how's everybody doing today? What are you guys doing to stay not crazy during this period of being trapped up in your houses? Besides your school, I know you're spending hours and hours working on integration problems, so besides that, what are you guys doing to stay sane? Or maybe you're not. Should I ask your parents what you're doing to stay sane, or at least whether you are staying sane?
I had a question about the test.
Yes, good question. Good thing to ask.
So is it timed, or is it just supposed to be open, like, for that? Like, once you open it, is it timed?
Yes, I don't know, actually. I meant to look into that. For sure, there's going to be a free response part, and that part will not be timed. So I'll have a couple of free response questions for you guys, and that will be, I'll make them available like 24 hours in advance, and then you have as much as 24 hours to work on them. There's going to be a quest part as well. I haven't investigated that to see if I could make it be so that you have like exactly 1 hour to work on it after you open it. If I can figure out how to do that, I guess that's what I'd like to do. But I'm actually not sure that I know how to make that happen. Can I answer your question on Wednesday, maybe? Brianna, that's a good question, but I'm afraid I don't really have the answer.
Yeah, that'd be great.
But I mean, correct me if I'm wrong, but it sounded like you guys wanted an exam that was structured like the one last time, where there's at least a couple of free response questions for you to get partial credit, and then some multiple choice ones where you're free to guess. There's no penalty for wrong guesses. But it is a test, so there won't be any free tries on the multiple choice. You just make one, whatever choice you have on there. When you hit submit, then it's done. And actually, people were asking me too about the material that's going to be on the test. So it will be everything since the last exam up through and including the material that's on this homework that you're working on right now. So in other words, I do want you to be able to compute integrals. Well, first of all, integrals over subsets of the plane, some of which might require a change of variables. And then integrals over these paths and surfaces that float in 2 or 3 dimensions. And we're in the middle of describing how those things work, so we'll do more of those today. I would also like to include line integrals, which we haven't mentioned, although as I'll explain, they're after a little step, they're the same as path integrals, or even easier once you get used to thinking of what they're supposed to be. Other questions about the test. So that'll be on Friday. The test is on Friday. And by the way, that will mean we will not meet as a class on Friday, because I'm going to assume that you're working on the exam during our regular class periods on Friday. So we'll meet today and Wednesday, and you can keep working on the, practicing the problems and using Piazza or whatever up through Thursday, I guess, whenever I make the test available. when it is available, I'll send you guys the questions by, I'll put them up online on the course webpage. I'll put a link to it on Canvas. You'll get an email that'll have a link to it as well. We don't know how this is working. Everything this semester is all kind of an experiment, so we're doing our best. So that's the exam. What do you guys want to ask me about the homework? Any of the homework questions giving you special trouble? No, really? Okay. Well, let me show you the context of what we're working on, and then we can push forward a little bit today. So I tried to make a little schematic of the different topics. Out here. Okay. All right. So we spent a fair amount of time doing path integrals. To have a path integral, somebody has to actually give you a curve, I mean a finite length curve presumably, and a function that's defined on that curve. Again, usually the function is defined in terms of the x, y, and z coordinates of the points that you're passing through. And it's the same deal, always chop things up, multiply values of the function times the size of the pieces. The size always means length, so I've been writing like a dl. By tradition, those path integrals are usually written with ds. I'm not even sure what the s is supposed to stand for, but that is an indication that you're measuring the sizes of the pieces by length. The little differential that is written on there at the end, it's really not critical how you write it, but usually there is a clue in there that'll help you realize whether you're supposed to be multiplying by units of length or units of area or units of volume. Anyway, our mechanism for computing these things just always starts by parameterizing the path. You write the x and y coordinates, or x, y, and z coordinates if it's in 3 dimensions. You write them all as functions of time. And then after you've chosen the parameterization, then you have to change 3 things in the integral. You change your region of integration so that it becomes a portion of the t axis, the t real number line. You rewrite your function so that it's all expressed in terms of t by making these substitutions. And then finally, you have to account for the fact that an interval in the t-axis does not have the same length as the corresponding arc portion of this path. And there's a fudge factor in there, which I tried to describe to you last time, is just measured by the magnitude of the velocity vector, the magnitude of the derivative of phi. Now, if you guys are good on path integrals, then there's actually 2 ways that you can turn next. And the book wants us to next discuss line integrals, and I have instead jumped ahead to discussing surface integrals. So let me show you how all that plays together. The concept from chapter, what are we in? Chapter 7 is all about computing these integrals over things that are not just chunks of Euclidean space, but rather a skinny portion of a high Euclidean space. So that'll include both paths that are in 2 and 3 dimensions and surfaces that float around in a 3-dimensional space. We've hit this one pretty hard, and you've seen the connection with the, with the parameterizations. So I thought it would be more natural to go next to the surfaces, because those are calculated, those integrals are calculated in the same kind of a way. I mean, the idea of what they represent is the same. It's chopping up and it's measuring areas of the pieces times the values of the function. And it's computed in a similar way as well. You begin by parameterizing. In this case, you parameterize a surface. So the x, y, and z coordinates are represented as functions of u and v. You need 2 parameters to parameterize a surface. 1 parameter for a curve, because a curve is 1-dimensional. 2 parameters for a surface, because a surface is 2-dimensional. Everything works pretty much the same as before. Your region, your surface is parameterized by a region in the UV plane, just like I had a region in the t-axis before. So you'll rewrite the integral as an integral over that region. You'll make some substitutions into the expression for the function. And finally, you need to adjust this area element because an area in the UV plane corresponds to an area of a surface that'll have a region of the surface that'll have a different area. And the fudge factor I explained to you last time, but we didn't do any examples. The fudge factor in this case is given by computing a cross product of some partial derivatives. So I want to make sure we do an example of that to get us rolling today. At the same time, there's a different way to generalize what we had done for path integrals, which is a very common application of these things occurs when the thing that you're adding up as you move along a curve has to do with things like people fighting a force. Like if you're riding a bicycle into the wind, then you have to do a lot of work to move from point A to point B. And the amount of work is dependent on the path that you choose, and it's also dependent on the force of the wind as you fight it. And we ran into this situation before when we were discussing vector fields. And we talked about the fact that in some cases, the amount of work that you were going to do would depend on the path that you were going to take. In this chapter now, we're actually going to be able to do those computations and figure out how much work is going to be necessary, how much work we're going to do. And that will lead to something that's called line integrals. I know the word path and line sounds very similar, and the notation for these things is pretty similar. But in all of these calculations, you have to first start with a force, which is a vector field, and then do a computation to change that into a function that's to be integrated in the way that we did over here. So in the book's presentation, they jump into this next after they discuss path integrals, but I think it's going to be easier for you guys if we focus on this and get all of these things done first where there's no references to the vector fields. So that's where I'm going to do it for a while today, and then at about the halfway point today, we'll see what the connection is with those vector fields. And by the way, I'll do this stuff today where we have the vector fields interfacing with curves. There will be more stuff that will also integrate that was a little unintended pun, integrate the force fields with surfaces as well. So that's kind of on this lower level, but that'll be after the exam. All right, so let's do an example of a surface integral, because I do want to show you how you get through those computations that have those cross products in them. So I've drawn a fairly simple example here of a circumstance where we would run into computing a surface integral. I would like to compute the area of a little patch of a surface that's floating in three-dimensional space. Specifically, I'm going to get this surface by intersecting a plane that's, I've got here the plane of points that have z equal to 3x. I'm going to intersect that with the interior of a cylinder. And here the boundary of that cylinder is the set of points where x squared plus y squared is equal to 4. Just because I want to keep emphasizing this till the end of the semester. When I write down an equation that has multiple variables in it, you should always be subtracting the number of variables, the number of the space you're in, which is 3 here, minus the number of equations to get the dimension of the solution set. This is one equation in 3 variables. 3 minus 1 is 2, so that's a surface. You know the plane is a surface. Likewise, that's one equation in the 3 variables, so that describes the surface as well. That surface is the exterior of the cylinder, but I'm interested in the interior of the cylinder, which is not represented by an equation, but rather by an inequality. The interior would be the set of points where, should I draw a little fuzzy thing here? This would be the set of points where x squared plus y squared is less than or equal to 4. So it's an elliptical disk, actually. It's a flat thing that's bounded by an ellipse. That elliptical disk sits in the plane of points where z is equal to 3x and x squared plus y squared is less than or equal to 4. And to get the area of this region, well, areas can always be found by just integrating 1 over the set. You integrate 1 with respect to area over the set S. So, hang on, my phone is making all kinds of noises. Sorry about that. I think I shut it off. Okay. All right, so let's try to compute this integral. The first step in computing any surface integral is to parameterize it. I'm going to give you two different parameterizations. So one of the parameterizations just comes from saying, oh, you are just graphing this function of x and y. Here's a function of x and y, and we want to look at all the points where z is equal to that function of x and y, but only the portion of that graph that lies above this disk. Oh, Malik, you have a hand up.
I'm sorry, I'm just a little confused on like the picture and like what exactly to find.
Okay, I did my best. I don't know. I tried to draw this with the solid the solid arcs are things that you're supposed to be able to see, and everything that's dotted is actually behind something else.
I think I can't really see the dots. I think that might be the problem. It might be the quality of the webcam.
Well, all right. Maybe I'll darken it in as I go. So here is, well, it's just a parallelogram, of course, but this is supposed to be part of the plane. And I would graph this by first drawing, since I don't see y listed here, an easy way to graph this is to go into the xz plane and draw the line of points that have z equal to 3x, so that's a fairly steeply sloped line. And then, again, since y is not mentioned, you just stretch that out in the direction of the y-axis to get the whole plane. So that's the solution set to z equals 3x. The solution set to this other equation is a cylinder that pierces the plane. So I drew a perspective sketch of a circle at the top, and here's the straight lines that come from stretching that circle up and down. So where the two of them meet, there's actually an ellipse. It's an ellipse that's in the plane. Well, it's simultaneously in the plane and on the cylinder. And the dotted lines go in the back here, because you wouldn't be able to see the back half of that ellipse. It would be hidden by the cylinder. So then I want the region, the patch of the plane that kind of mixes, that blends, how should I say, just attaches the ellipse is the perimeter of this surface. Is that any better?
Yeah, I think that helps.
Yeah, you know, if you guys were right in front of me, you'd see me moving my hands around and slicing like this, but it's all very three-dimensional, so I'm doing my best. Slice a cylinder at a slant, and you should get this elliptical disc. All right, so I got to parameterize this, so I'm going to do it in two different ways that you guys might think to approach this integral. One way that you can do it is to say, oh, you're just graphing the function 3x over a portion of the xy plane. Specifically, in the xy plane, I don't know if you guys can see this, but I drew kind of the equator of the cylinder. That's the set of points in the xy plane that have x squared plus y squared equal to 4. So that's a circle of radius 2 centered at the origin. And above, or I should say above and below that surface, that's where you're looking at the graph of this function. And you're trying to describe that graph. How do you parameterize a graph? Now, when we were parameterizing the graph of a function of one variable, our cheat was to say, look, if you're going to write y as a function of x, and you need to parameterize it, just let x be the parameter t, and then y is whatever function of t you need to stay on the graph. In the same way, I can always parameterize the graph of a function of two variables by just using the two variables as the two parameters. Let x just be u and let y just be v. So they're just synonyms. And then as u and v vary, now you'd have to have u and v varying over this disk. If you take combinations of u's and v's that have u squared plus v squared less than or equal to 4, then you would get points in three-dimensional space that have x squared plus y squared less than or equal to 4. So this is a kind of a quick parameterization that you can get anytime your surface happens to be the graph of a function of two variables. Let x be u, let y be v, and then of course z has to be computed by whatever formula you're using to make the graph. So in this case, if z is supposed to be 3x and x is just u, then z will be equal to 3u. Well, okay, so now I've got my parameterization. What do? You always have to change the three things that show up in the integration problem, figure out what the surface S corresponds to in the UV plane, and as I said, you'll get all the right combinations of x's and y's, or x, y's, and z's, by taking u's and v's inside this disk. So this is the portion of the UV plane that I'm going to integrate over. Second, you have to take your integrand and make these substitutions for x, y, and z to get yourself a function of u and v. But, well, there's no x's, y's, or z's involved. I mean, this is 1 plus 0x plus 0y plus 0z, if you like. So forming the composite is still just going to give you a 1. That's easy. That's the second part. And the third part is this area element, because when I take portions of the UV plane and try to map them into sections of this elliptical disk, effectively what I'm doing is I'm taking a portion of that disk that's on the XY plane, on the floor, and I'm projecting it upwards to the slanted elliptical disk. And when you do that, there's a certain amount of stretching that the portions that are over here will have to be sent up higher than the portions that are near the middle, which don't get raised at all. So stuff gets stretched. The stuff that's along the x-axis will get stretched upward. So you should understand why there has to be some change of areas from the UV plane onto that slanted plane. But we have a formula that tells us, this is what we discussed last time, how do you get that fudge factor? And that comes from this, what I explained last time is it's the magnitude of this cross product. We recognized from the beginning of the semester that this cross product would give us the area of a certain parallelogram, and that's exactly the parallelogram that you get by raising this little rectangle up to the slanted plane. So let me pause here. Kyle, you have a question.
Could you explain what the t is representing when in the 1 times t and where to go between the first and second step?
That's not 1 times t. It's 1 composed with t. That's an open circle there. It stands for.
Oh, okay.
Yeah, thanks for asking. So what we always do when computing an integral is to take the function of x, y, and z that's presented and substitute in these formulas for x and y and z. And like I said, this particular example has no x, y, and z in it. So there's nothing to substitute. So you still just get a 1. Is that clear? I mean, maybe I should say this right here.
That makes sense.
T. This t takes the 2 input variables u and v and creates 3 output coordinates x, y, and z. All right, so what we didn't do last time is to actually do a computation of this. So let me just point out how this works. So this function t is a function from R2 to R3. It has a derivative, which is a 3 by 2 matrix. It's 3 rows because you're going to differentiate each of these 3 functions, and 2 columns because you're going to differentiate each one of them with respect to the 2 variables u and v. The t sub u just means I want that first column. I want to take the partial derivatives of each one of these things with respect to u. And you can see that I've done that down here. The partial of the first is with respect to u is a 1, and then a 0, and then a 3. And likewise, the t sub v means the derivatives with respect to v, which are 0, 1, and 0. If you put these 2 columns together, you would get the entirety of the derivative matrix t prime That would be your 3 by 2 matrix. Oops, let me just cross out the little cross. So that's the T prime that's in there. And our discussion last time about areas, I invite you to go back and listen to that again. We saw that we would be getting the areas of the parallelograms that correspond to these rectangles by, well, our calculation for the area of the parallelogram asks us to take the cross product, the magnitude of the cross product of the vectors on the two edges of the parallelogram. So I computed this cross product the way that's easiest for me. I like to write things in terms of I, J, and K, and then this cross product was easily done. It comes out to K minus 3I. I know some of you prefer to write down the 3 by 3 matrix that also has an IJK in it. Have at it. However you like to compute your cross products, this is what you should get. And then the magnitude of this vector happens to be a constant. It's square root of 10. So I've transformed the entire surface integral expressed in terms of x, y's, and z's into a new integral expressed in terms of u's and v's. We're integrating this function of u and v, happens to be a constant, over this region in the UV plane. And by Fubini's theorem, that can be computed by doing a double integral. Or it's actually faster in this case to say, well, duh, if you have a constant that you're integrating, just pull the constant out, and then you'll be integrating 1 over this region D. And as you guys know, every time you integrate 1 over a set, you're calculating the size of that set. And since D was a disk of radius 2, the area is pi r squared, which is 4 times pi. Multiply that by this constant that we pulled out, and this is my final value for the integral. So that would be the area of this slanted elliptical disk. I've computed it as an integral, but it's a surface integral of a surface that's floating in 3-dimensional space. Want to ask me any questions? Any more? All right, let me show you that I want to do exactly the same integral, calculate the same value. I still want to get that same answer, but I want to do it with a different parameterization.
Dr. Rubin, could you show the integral one more time for the previous example? Thank you. Okay, I see you. Thank you very much.
Okay.
Could you use cylindrical coordinates
for
this?
I can use a different coordinate system, but not cylindrical, because cylindrical coordinates are a way to find your way through all of 3-dimensional space. I mean, you sort of can, but I don't know quite what you intend to do. It's not really a question of coming up with a different coordinate system. What you should say is it's a way of establishing a coordinate system on the set you're trying to integrate over. So you wouldn't use cylindrical coordinates on a flat disk. I mean, I know it's a slanted disk, but it's just a surface. You find your way on a surface with 2 coordinates. That's why it's called a 2-dimensional set. I know it sits inside 3-dimensional space, but to determine your location, whatever your coordinate system is going to be, you would need 2 coordinates. Or that's the same as saying you parameterize things with 2 parameters. So I will give you something that maybe will feel like cylindrical coordinates, but it's not. It's just a different parameterization of the surface.
So even though it's a slanted, like a slanted ellipse in 3D space, it's still just a plane. Like it's still just a flat object. So it's 2-dimensional.
Correct.
Okay.
So I know everyone likes to say a sphere is a 3-dimensional object. It is in the sense that it lives inside 3-dimensional space, but mathematicians think about a sphere as being a 2-dimensional object because we would determine a location on the sphere with just 2 coordinates. Typically latitude and longitude would do. So if you can tell where you are with just 2 numbers, you've got a 2-dimensional set, which is AKA a surface.
Yeah.
Okay. So, and that's the language I've been using since the beginning of the semester when I've been having you guys count variables, count equations, and subtract to get the kind of intrinsic dimension of the solution set. Three variables minus 1 equation would leave 2 as the dimension of your set. It's 2-dimensional. You're going to need 2 parameters to parameterize it. And I did
Okay.
it here with the u and v, but I could use two parameters. Again, I'll call them u and v, or you could, you'll see, you'll be tempted to call them r and theta. But whatever you call them, there will be two of them in any other parameterization. So maybe this is the kind of thing that you would be thinking of when you think about cylindrical coordinates. I can tell you any point in three-dimensional space by giving it cylindrical coordinates called r, theta, and z. So then the x-coordinate would be r times cosine of theta, y would be r times sine of theta, and z would be z. Just leave it as a z. But then the fact that you're restricted to being not just anywhere in three-dimensional space, but specifically on that little disk, well, that's going to restrict your r-coordinate for sure, and it'll also restrict your z-coordinate. So yeah, I'm kind of thinking of cylindrical coordinates, but it's a little better if you think about it as a parameterization. Off somewhere in a distant land, you have a two-dimensional space that's got u's and v's as its coordinates. So those are the labels of the axis. And then I'm transforming all of these points. Every combination of u and v gets transformed into a combination of x, y, and z. Every point on this plane gets sent to somewhere in three-dimensional space. And if I use those two coordinates, those two formulas to spit out my x and y coordinates in this picture, then I have a sense of exactly what u's and v's I need. I mean, you know, from the way trigonometry works, you'll just need to take all the v's possible between 0 and 2 pi. And then secondly, if you want to stay on the inside of this cylinder, you need to have your u coordinate stay less than 2. And so that's what I've done in this picture. I've shown that I already know the combinations of u's and v's that I need just to make the x's and y's range over the right set. But I still need to stay in that slanted plane over here. So I still need z to equal 3x. And if my x-coordinate is given by this function of u and v, then the z-coordinate has to be that function of u and v. So is this better than the previous parameterization? Well, it does give me a rectangular region to integrate over. That's nice. From when we get down to having an integral with u's and v's in it, it's nice, by Fubini's theorem, it's nice if your region of integration is a rectangle, because then you just have constants, what you'll see over here. You'll have constants as your limits of integration. On the minus side, these formulas are certainly more complicated than the ones that I had a few minutes ago, so maybe you would like this parameterization better. I don't care. You can use either one. You can use some variation of those. You could have put in 2 pi's in front of the v, and then your v would just go from 0 to 1. Some people like that better. I just want to illustrate how we would go through the process of rewriting the integral. I mean, as before, you say that the area that you're trying to compute can be expressed as an integral over the surface. But then to compute this integral, you're going to have to rewrite both the region of integration and the integrand and the differential in terms of u's and v's. I've already figured out the region D I need to integrate over. It's this rectangle. The integrand has to be changed, as always, by replacing the x, y, and z by these formulas, but we're kind of off the hook because, as I said a few minutes ago, there are no x's or y's or z's in here. So that just stays as a 1. But then finally, the area element, this differential dA, needs to be computed as the magnitude of the cross product that you integrate with respect to u and v. So here I've done it again what I did the last time. I took this function that goes from R2 into R3, that's what capital T is. Its derivative would be a 2 by 3 matrix, I'm sorry, a 3 by 2 matrix, which it's going to be, this is its first column and that's its second column. You just differentiate these expressions first with respect to u, which is the easy part, and then with respect to v, which requires some trigonometry, calculus of trig functions. And then you need to take the cross product of these two vectors and take the magnitude of that. Well, I did the work for you. When you take the cross products of these things, you know you multiply various elements here times various elements there. There's a couple of such pairs for each one of the coordinates. Those trig identities come to your rescue in a couple of those cases. To get the middle coordinate, you'd be taking cosine times negative sign, and then minus cosine times negative sign. So actually those just cancel and leave you with a 0. So that's what I get for the cross product. And when I compute the magnitude of this cross product, I see that there's a factor of u that I can pull out, and actually an absolute value of u, and then the rest of it turns out to be a square root of 10. You shouldn't forget the absolute values, although in my particular case, all of the u's in question range from 0 to 2, so the absolute value of u is not actually needed. All right, Kyle, you have a question? Or did you?
Where does the u go in the integral below it? Because below we only have the 1, and we can just factor out the constant. But when we're actually doing that magnitude, we get that u, that root 10u.
Whoops, you are correct. I wrote the wrong thing. There is a factor of u in here. That should be u. Thank you.
Okay, and what were the bounds of integration for the other method?
Well, I never actually wrote them out because I didn't feel like using Fubini's theorem here. I should have said that u goes from -2 to +2, and for every value of u, the v will go from the negative square root of 4 minus u squared to the positive square root of 4 minus u squared. So this would have been a kind of a nasty looking double integral in this case. I'll write it for you. It's the integral as u goes from -2 to +2, and then v, for each one of those u's, v will go from the negative square root to the positive square root. But I just skipped all of that because I recognized, oh, I'm just integrating, after I pulled that constant out, I was just integrating 1 over a region. And when you integrate 1 over a region of the UV plane, you just get the area of that region. Oops, so it should be a square root of 10 du dv. So if you want to write it as an integrated integral using Fubini's theorem, that's what you would have. And that looks pretty nasty. I mean, we know it's not going to be too bad, but sorry, I seem to have v's on the inside and u's on the outside. So yeah, that's what you would be stuck with, precisely because this region of integration is not a rectangle. And by contrast, this region of integration was a rectangle, so my limits of integration are just constant, 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 constant. And I guess I should have gotten a u squared over 2. Sorry, I get u times v. No, I see v is on the inside. Wow, I was not very careful. So when you integrate with respect to v, you'll just get 2 pi times u. Now you integrate with respect to u, you'll get pi times u squared. When you stick in that value of u and that value of u, that'll turn into 4 pi. There's that square root of 10, and it all comes out. So yes, thank you for catching my error. I forgot this u. I don't know why I did that. If you didn't put in that factor of a u, you'd be off by a factor of 2 or so. So you would recognize you didn't get the right answer. All right, you guys good with that? So those are surface integrals. And as I said, this particular example, in this particular example, the surface we're looking at happens to be the graph of a function of x and y, or the portion of that graph that floats over some region in the xy plane. And that's not an unusual circumstance. So I wrote out what would happen if you did that in general. If someone says, hey, please integrate over this surface S that's floating around as part of the graph of some function g of 2 variables. Now that's not the f. F is the function that you're integrating on that surface. So in our previous examples, f was the constant function 1, and g was the function 3x plus 0y. And the d that we had before was some disk or something like that. And my suggestion on the first, on that first option of those 2 ways of parameterizing it, as I said, why don't you just let x be u and y be v, and then z just has to be whatever function of x and of u and v is dictated by this, by saying that you're on the graph of a function. So in that case, what are we going to do? The region of integration in the UV plane, the UV plane is really the same as the XY plane. So the region of integration will just be the same set D. The function will be rewritten in the way that we've been always doing it. You just replace the X's, Y's, and Z's by the U's and V, the formulas involving U and V that I've written down over here. I'll come to that in a second. And then the little fudge factor is always this magnitude of a cross product. But if your parameterization is this simple, X is just U, Y is just V, and then only the Z is complicated, then the partials with respect to U and V are pretty easy to figure out. The partial of X with respect to U is just the number 1. The partial of that with respect to U is just 0. And this partial is whatever it is. I mean, you take that function of U and V and you just differentiate with respect to U. And likewise, the other partial derivative is easy to compute. Partial here is 0, partial here is 1, and then the partial here, I just write it down. And with those two vectors, those two columns being fairly simple, it's not hard to compute the cross product. I just get exactly this expression, a 1 for your third component, and the other two are essentially just those two partial derivatives. So in that setting, here's how your integral, your surface integral is going to get rewritten. You'll change your region of integration from being the floating surface to its shadow, its projection down on the XY plane. You'll have to rewrite your function because, well, all the Z coordinates have to be rewritten in terms of X and Y, but the X and Y themselves can just be left as they are. Only the Z needs to substitute in, like I substituted into our previous one, I would write in Z equals 3X because that's the function I was graphing to get the slant. And then finally, the magnitude of this cross product is just the square root of the sum of the squares of its components. And I decided to rewrite them because you see this formula written out sometimes. It's the square root of 1 plus, and here's the sum of the squares of the two partial derivatives of the function that you were graphing. So in our previous case, this would have been the partial of Z with respect to X was just 3, partial of Z with respect to Y was 0. And that's why all this stuff gave me the square root of 10. So in the special case where the surface that you're integrating over is part of the graph of a function, you have a separate formula that you can memorize if that's easier for you. I personally don't like to memorize extra formulas, but it does save you a little time, I guess, instead of recreating all the special calculations that I've done here. So if you want to keep that as a separate formula to memorize, that's your choice.
Dr. Russell?
Certainly, go ahead.
Is it del Z over del Y, or is it del G over del Y?
Well, I guess I don't know the difference. I mean, here in this example that I did, this is the function that I'm calling G. So what I want you to put into this spot right here would be the 3. Are you thinking of that as the partial of Z with respect to X, or is that the partial of G with respect to X? It's going to come out to be the same thing.
Okay, yeah.
Yep, so it's just a notational change. All right, before
sorry,
go
sorry,
ahead.
Dr.
No,
does the second one, does that say DZ over DU?
No, well, dz over dy is what I meant. Although, yeah, dz over dy. Let's just
And
call
then
it.
the first one is DZ over DX?
Yes. Yeah, those are the derivatives indicated here, except that and since in this kind of a parameterization, I'm thinking of X and U as being synonyms, and Y and V are also synonyms for each other. So I can kind of go back and forth. The usual way of saying everything where you have the UV plane kind of separate from XYZ space, that's where you're expressing all of your integrals in terms of U's and V's. But in a picture like this, a lot of students prefer to say, yeah, I don't need new letters. My parameters are just down here in the XY plane, and my parameterization just takes each point in the XY plane and it goes straight up. keeps the x coordinate unchanged, keeps the y coordinate unchanged. It just calculates the z coordinates from x and y. And if you're in that mode of thinking, then you're just going to rewrite your integrals, keep it all in terms of x's and y's. You just get rid of the z's where they show up, anywhere that they show up inside the function that you're integrating. Your region of integration has just been pushed down into the xy plane. And then you just have this fudge factor that takes into account the slanting that occurs when you go up from the bottom, the flat bottom, up to the slanted surface. This is how much areas get lengthened. There'll actually be a lengthening all the time. They get lengthened by a factor of square root of 1 plus the sum of the squares of those two partial derivatives.
And that says dx dy at the end. Right?
Yes. Yes, so people who like to think of x and y as the parameters themselves, they'll write dx dy at the end. When I did it in this example, I actually had new names for the x and the y coordinates. I called them u and v, so that's why I ended up with du dv at the end, or dv du. Okay. I got one more thing to say about surface integrals before I turn to those line integrals. And that is, you know, sometimes the surface, I didn't have a good way to say this, sometimes the surface you're looking at is just a set of points that's actually already in the xy plane. I mean, it's a part of three-dimensional space, but what if the z coordinates are always 0? Well, then the way you would parameterize it is just the same sort of thing that I did here. You just use the x and y coordinates as your parameters. I mean, you're parameterizing the set with itself. Or you could say, but I have too odd of a shape here. Like maybe my region that's floating in three-dimensional space happens to be like a quarter of a disk that's down there on the bottom of, on the xy plane. So if that's my set S, maybe I'd like to parameterize that with two parameters u and v that might give me a region of the uv plane that's just a rectangle. In other words, I would write x and y as functions of u and v, but I'd keep my z coordinate as being a 0. Nothing wrong with that. Just because my z coordinates are all 0 doesn't mean I can't use all this previous theory. And just because I'm in the xy plane doesn't force me to use x equal to u, y equal to v. I could use any other parameterization I like, just like I did in this setting. Well, if you then go through all the steps, here's your derivative, and when you take the cross product, those zeros give you a couple of quick zeros in the cross product. The only term in the cross product that survives is this one right here. And so the magnitude of this cross product turns out to be just, well, the absolute value of this expression right here, which you should recognize is the determinant of that 2x2 matrix. So for those of you who are asking me, how come it's determinants that show up in the change of variable theorem? This is the reason. That change of variable theorem that we had can be thought of as this special case of how to integrate over a floating surface. If your surface doesn't really float, but it's just on the xy plane, just do exactly what we've been doing, but realize that you get a bunch of zeros that simplifies everything except for this one last fudge factor, and that turns out to be the determinant. So anyway, set that aside because it doesn't actually give you any new tools. All right, what I do want to do is to set you up for these line integrals, which is the last topic that we need before the test. So here's the deal. I want you to envision that you're walking or riding a bike or something like that, and you have a force that you have to fight, some sort of wind, but it's a force that's coming at you in three-dimensional space. In order to figure out how hard it is for you to do the work of moving forward, I mean, you know that you should be able to compute the amount of work done by taking the force that you feel times the distance that you travel. But the force that you feel isn't quite the same as the force of the wind. It's not the magnitude of this vector. If you're trying to go that way, and the force is blowing at kind of an angle on you, then the amount of force that you feel will just be, it's the magnitude of that force reduced by the value of the cosine of this angle. Whatever this angle is, that's the difference between the angle that it's coming in and the angle and the direction that you're moving. Moreover, the direction that you're moving, well, it's the force that you're going to feel. It kind of makes a difference whether you're moving forward or backwards. All right, it's nice to have the wind at your back instead of at your face. So you need to take into account the direction of your motion. You need to take the unit vector of your motion, which is either going to be the forward direction or the backward direction. This product in here can be thought of as the dot product of F with the unit vector in the direction that you're moving. And that could be written by taking your velocity vector divided by its magnitude. This dividing by the magnitude gives you the unit vector. The vector itself is going to be either that forward direction or that backward direction. So when you want to calculate, oh, actually, I guess I should be clear too. If you're moving in the forward direction and the wind is blowing backwards, that's when you feel a force. In general, if the let's see, how do I want to say this? I want a minus sign in here. If the force, right. If the wind is blowing like this and your velocity vector is like that, then the dot product of these two vectors will be negative, and yet you're feeling a positive force. So it's actually going to be computed as the minus of this, the negative of this. Here, let me put a minus sign in here, where u is equal to the unit vector in the direction of motion. All right, so this is the amount of work that you have to do for every step that you take. If you want to figure out the total amount of work that you have to do as you move along a path, you would write this in exactly the way as we've been introducing other integrals. You would say, oh, well, you just need to integrate along this path that you're trying to travel. This is the quantity that measures the force, the amount of work that you have to do per step. You multiply the work that you have to do per unit distance times the amount of distance that you travel as you perform that much work. So all of this crap inside the parentheses, all of this delicate mathematical material that I have inside the parentheses, I'll just call that little f. And that's a numerical quantity that you need to integrate as you move along the path. You find the vector field that indicates the force that you're fighting, and you take the dot product with this unit vector to get this extra factor of a cosine in there. That will reduce the amount of work that you're doing depending on whether you're fighting the wind or not. So if somebody asks you to compute this kind of an integral, they're asking you to, so there's a vector field involved, but it gets reduced by taking the dot product with this unit vector. So you'll see different notations for this. People will say, I want you to integrate minus f dotted with u, where u is the unit vector. Or they'll say, I want you to integrate minus f dotted with, and then they'll write ds as a vector, where they mean, yeah, I want you to take units of length, but also keep into account the direction in which you're traveling. And that little piece of motion represents a small displacement in the x direction and the small displacement in the y direction. So you also see this notation where people say, yeah, write this thing out as a vector that has two components. You write down the x component of the vector field and multiply that by dx. And likewise, you figure out the second component of that vector field and you multiply that out by dy. So these are all different notations, but they all mean the same thing, and therefore they would all be computed in the same way. You're going to always get these by parameterizing this curve, sticking in your formulas for x and y, or x, y, and z into the function f, and then multiplying by the fudge factor, which is the magnitude of the velocity vector, integrate that with respect to t. And I know I've gone over, but I can't resist showing you that when you do all of that, you're going to be integrating this function, reevaluated as a function of t. You'll be taking the dot product with the unit speed. So here's your unit velocity, here's your velocity vector that you then have to divide by the magnitude of the velocity vector. And then at the end, you've got the fudge factor that says, oh yeah, you have to multiply by your speed vector and integrate that with respect to t. And here is a tremendous gift from nature. This extra fudge factor that I just stuck in there cancels the thing that I put in the denominator to get a unit vector. So your computation actually just results in you evaluate this vector field at the points that you're traveling to, and you dot that with your velocity vector. You don't have to compute magnitudes because the two times when you would cancel each other out. All right, I went way over. Yeah, if you have a quick question, I'll throw it in here, but this is where we're going to have to pick up next time.
Sorry, Dr. Usen, could you maybe just explain what the v over the unit vector v represents? Like, I understand the bottom equation, but I don't understand how they're equivalent. Like, those two representations are equivalent.
These two?
Yeah, like I don't understand how that's equivalent to like the dx dy that you wrote down below.
Well, each one of these was just rewriting. These are more just notational variations more than anything else. This is the one that you should, I would hope you would understand that this is where the actual integration is going to come from. The total work that you do is the sums of the works that you do on each little segment. How much work do you do on a segment? It's force times the distance. Well, how much force do you have to fight? It's not the magnitude of this force field, but it's that magnitude shortened a little bit by the cosine. So that's how I've computed the work that I do per unit distance as when I'm at one little portion of my curve. When you actually want to compute this integral, don't think about all this stuff in the box as being something complicated. It's just a function that you're evaluating at each point in space. As I go to actually evaluate this integral then, you know how I do it. I have to parameterize the curve, and then I figure out the corresponding range of t's. I didn't even write them in. And I'm going to have to do a substitution into this function, little f, and then I'm going to have to multiply by the fudge factor. So it's these symbols that just say you're taking this function, little f, and you're evaluating it at each point that you pass through. So you replace every x, y, and z by phi of t. There's x, y's, and z's involved here. That's measuring the force field that you're feeling at each point. And there's also x, y's, and z's in here because when I'm at different points, I'll have different unit vectors pointing along the curve. These will always be the unit tangent vector to the curve. But the numerator is your velocity vector, and the denominator is there to turn that into a unit vector. Yeah, I know I didn't do a good job there, but I've gone way, way over now. So I'll tell you what, let me stop here. We'll pick up exactly here on Wednesday. And I'll also be available as usual today for office hours at whatever our times they are, 1 and 3, I don't even remember.
Thank you.
Okay? All right, guys, give it a shot. Make sure you can do the surface integrals, and then we'll finish the line integrals on Wednesday.